morning all again. Our next speaker is Louis Masson, a flight software engineer at CYSEC. Louis completed his Master of Science degree and his PhD in EPFL in Switzerland. And he has worked in the past for the Swiss Space Center. And now he's combining his academic experience with his passion in order to deliver the next generation of security solutions for the new space industry. Louis will talk about the demonstration of end-to-end protection of CCSDS satellite communications. Louis, the floor is yours.
Thank you very much for the introduction. So I'm here today to give you a presentation and demonstration of ARCA Satlink, one of the next products that will be launched by CYSEC this year. ARCA Satlink is a solution that will allow you to protect the end-to-end communication between your satellite and the ground stations. So before I get into the specifics of what this means, I would like to give you a bit of context into this. So as a lot of you may already know, satellite services are deployed through groups of satellites or satellite constellations, which are then connected to ground stations, which are then connected to servers, which are accessed by operators or clients. The issue with this is that you have a large infrastructure with a lot of endpoints, so it's a wide attack surface that is vulnerable for the taking for any malicious actor. So cybersecurity is not a new topic. We have solutions already in the industry that can be available to cover this part of the diagram. What I would like to focus on more specifically today is the upper part of the diagram. So to be more specific, the communication between satellites themselves and the ground. So this is where ARCA Satlink intervenes, because there's a lack of solutions that are easily implemented and are readily available in the market. And to give you a presentation of Satlink, I will first go into the SDLS standard, the Space Data Link Security, which our product is based on, after which I will give you a description of the product itself, followed by a demonstration, and we'll conclude with a few key points. So, Space Data Link Security is a standard formulated by the CCSDS, which is a consultative committee for space data systems. It's a consortium of international governments, government agencies, and of course industrial actors, which provide a whole ecosystem of standards which describe the whole communication stack between the satellite and the ground, all the way from the physical layer all the way up to the application layer. What I would like to focus on in these standards more specifically is the data link layer. So in this diagram here, really this row. So you have the very well-known telemetries and telecommands, which are industry-wide and industry-used, which allow you to send packets to and from your satellite, between your station and your satellite itself. And you also have a few others, such as AOS for Advanced Orbiting Systems and USLP for Unified Space Link Protocol. The reason I mentioned these protocols is because SDLS is grafted directly onto these protocols. So to understand how you can secure your link with the SDLS solution, you need to understand how SDLP, so Space Data Link Protocol frames, are formed. So this is what, in general, broad terms, an SDLP frame looks like. You usually have a frame body, a frame data, which carries the packets you are sending to and from the satellite. It is followed by a trailer, which gives information on error detection and correction. And it's usually prefaced by a header, which gives you information on the origin of the frame, on the channel you're sending it to, etc. So this is broadcast on radio frequency channels, and this poses a risk. So anybody with decent equipment, not that expensive, and a little bit of know-how, can intercept these frames. This poses two big problems. First of all, there's an issue of confidentiality. So anybody can access this frame, will be able to access the data that's carried within it. So the information which may be critical that you're sending from your satellite will be accessed by anyone. The second issue is an issue of authentication. So for instance, a satellite will not be able to verify that the frame it has received, which can be a command, comes from the intended operator. SDLS acts on the SDLP frames in two ways in order to affect this, these two issues. First of all, we have encryption of the frame data. So we are obfuscating the contents of the packet so that anybody who has the ability to intercept a frame but doesn't have the keys you use to encrypt it will not access the data. Second, SDLS can add some data constructs to the frame. So this comes at a cost of bandwidth, of course, because you're adding data to the frame itself. But this allows for the authentication of the frame. How does that work exactly? So the trailer that we're adding onto the frame itself comes with a message authentication code. This is used. This is calculated through authentication algorithms using a key, on the body of the frame itself in order to calculate the code, and the receiving endpoint can then compare the code he calculates with the one he receives to make sure that it comes from someone who has the same key as you. Additionally, the header comes with a bit of information for the receiving endpoint to understand how you decrypt the frame. So there are some parameters that are used in cryptographic algorithms, such as the initialization vector, but there's also some mechanisms like called the sequence number, which is used for anti-replay. I will get back into this a bit later. Most importantly, we have information about the security association. So this is the concept of SDLS, which is like a configuration of the secure channel. You can see it as a VPN configuration, which provides information on how this channel is secured. So you have information about the keys, the cryptographic algorithms, but you are also tracking the sequence number. This is something that exists on both endpoints, so satellite and ground, and it's maintained by both. This is important to see later on. In terms of interface, SDLS, as I mentioned, is directly grafted onto the SDLP, so the Space Data Link protocols, telecommands, telemetries. This means that we have procedures, baseline procedures, that allow us to secure frames. So first of all would be apply security, which is called by the sending end, which takes a frame that has not been secured yet and wraps it in secure features. Second, we have the process security, which is called by the receiving end, which allows the receiving end to unpack and decapsulate a frame from its secure features and access the data. In the process of generating frames, so a frame is takes packets, they are added on to a frame, then it's sent for encoding for error detection, and then finally it's sent over the RF link for modulation. The same steps in reverse order are processed by the receiving end. The SDLS standard procedures happen during the frame generation. So this really combines with what I said earlier. SDLS is directly grafted onto the SDLP protocols. In terms of services, you have a few management services that come with the SDLS standard. So you have a key management procedure, which allows you to rotate keys. You have security association procedures, which allow you to configure the secure channel. So you can change the algorithm, you can do channel configuration. And finally, we have a monitoring and control procedure, which allows you to monitor the security of the link and see if there are any events that have occurred onto it. So now that I've given you a broad overview of the SDLS standard, I can go into Satlink more specifically. As I mentioned, Satlink is based onto the SDLS standard for good reasons. First of all, the main advantage of doing this is that since the CCSDS communication protocols are widely used by the industry, the solution is compatible with a lot of already existing solutions, including the solutions that are not already secure but are already deployed in orbit. Since it's a software solution, Satlink can be deployed on all endpoints of the infrastructure, so satellites and the ground itself. And as a software update, you can easily update it on satellites that are already commissioned. Finally, one last advantage is that as a cybersecurity company, CYSEC has embedded some security features and security best practices into the product itself to allow anybody, any satellite integrator to be able to secure the link with the best practices that are available. So, as I mentioned, Satlink is a software library. It comes with a few different components that you can use. First of all, there are non-interactive services. So these would be the implementation of the baseline interfaces of the SDLS, so apply and process security. These services are used to secure and unpack security from a stream of frames. A stream of frames. And we're using a cryptographic backend. So to do that, we can use any cryptographic backend. We're agnostic to what the client uses. It can be a software backend, it can be a hardware backend. And we're using this backend to apply AES, GCM, encryption, and authentication to the frames. This comes with other services. So we have persistent data. We need to be able to store and keep track of the keys. We need to be able to keep track of the security associations themselves, which configure the channels. And we also need to have a way to log any events that occur onto the secure link. And finally, most importantly, we have management services. This allows any operator of the satellite to be able to configure the secure link and monitor what's happening on it. So, as a software solution, I mentioned that it is deployed on all endpoints of the infrastructure, but it comes with a few differences depending on where you're implementing. First, we have a ground version of the software. This is implemented on a ground gateway for the ground station, either as a container on the cloud or as an on-premise solution, depending on your needs. This is used and called by the ground gateway to secure and unpack the frame from its security features. And it comes with an API which allows the operator to configure the link itself. Frames are then sent over to the satellite, and on the satellite itself, SDLS is a library which is implemented for space that the flight software can use in order to let's say, encrypt the frames that they're sending down and to decrypt the frames. Now, the juicy part of the presentation, we'll be giving you a demonstration of the product at work. But before I get into this, I want to give you a few objectives for the demonstration itself. First of all, we want to show you that using Satlink, the confidentiality of the information is ensured. So whatever you're sending from your satellite is protected. We want to show you that everything is authenticated, so nobody can take control of the satellite itself through commands that they're sending. And finally, we want to show you a resistance to replay attacks. This I will get into during the demonstration. So all this will go to show that an external observer that is monitoring your link between the satellite and the ground through equipment that he may have will not be able to interfere with the satellite or access the data. The demonstration itself is implemented as follows. So we are simulating the communication between two endpoints, space and ground, by having one board, the STM32 that I have here with me, simulating the satellite itself. So we have embedded hardware running the Satlink library. And another endpoint which simulates the ground endpoint, which is the a container running on the Amazon Web Services cloud. Both endpoints are preloaded with frames that they'll be sending to each other. And more importantly, every communication from the TC channel to the TM channel are done through TCP sockets. So we've grafted Satlink onto these two endpoints. So this allows us to secure the frames, telecommands and telemetries on both sides. And we are in a simple case scenario where we have pre-shared keys and security associations. It's still important to keep in mind that the security associations are maintained by both endpoints. So any change in sequence number will be stored by the different endpoints. Finally, the most important part, we have a window onto this communication, which is link proxy, which runs on my computer, not on the STM32 and not on the container in the AWS cloud. This allows a few things. First of all, it simulates what an external observer will be able to see if they were sniffing packets coming to and from both endpoints. So basically, we can see every packet that's transitioning through the secure channel, and it also allows us to have a few, let's say, attacks. So it allows us to replay frames, tamper the frames, and also permutate the order of the frames. A bit of a visualization guide. So this, what you're going to look at looks like this. To be a bit more explicit, so if you keep in mind the schematic I've shown you earlier, we have a window in the middle which shows the link log, the link proxy. So this is what the attacker sees. Then we have windows for the space endpoint and for the ground endpoint. Finally, one important thing to keep track of is the security associations themselves. So for each endpoint, for each channel, telecommand and telemetry, we are storing the security associations and we're displaying them here. Finally, just for visualization, we're color coding the frames. So clear data is always in blue, encrypted data is in green. The headers of the frames themselves is in pink, and we have the data constructs added by the SDLS, which are in orange. So unfortunately, we've had a few issues connecting the STM32 board to the Wi-Fi. So what you'll be seeing are pre-recorded videos of the demonstration. So welcome to the demo. This is the interface I showed you just earlier. To give a first example of what's going on with this demonstration, I'm going to send one frame from the space to the ground. So what you're seeing here is we have a frame with its header, in pink. It's data, so it's a string of 2 for telemetry and a string of 1s for telecommands, just for simplicity's sake, sorry. And this is sent over to the apply security procedure. What's happening then is we have an intact header, we have encrypted frame data, and then the headers and trailers from the security protocol are added onto the frame. So as you can see here, this frame, which has been secured, is transferred over to the other endpoint. What's important to notice is that you have the link proxy, which displays the frame as you would see it if you were sniffing the packets in between the two endpoints. On the other side, you receive the frame, and as it has been secured, it's sent over to process security and it's decrypted. So we are accessing the data in the end on the other endpoint. Now, in a normal situation, we would be sending frames to and from both endpoints simultaneously. So it will look like something like this. What's important to see here in this example is you can see the security associations between being managed by both sides. So for example, for the telecommands, it is first incremented by the ground before being sent up to space. I'm going to replay this real quick to be able to witness this. So every time ground sends a frame, the sequence number is incremented, and as it's received and accepted by space, it is incremented on its side. This is important because one of the first things someone can do when they're listening to your communication is try to replay frames that you've sent to the satellite. These could be critical telecommands which rewrite parts of the memory or do some potentially harming operation commands like turning off the thrusters or this sort of thing, which would deteriorate the orbit of your satellite. So the sequence number, this is where it comes in. If you replay a frame, it should be not accepted by the SDLS standard because the sequence number keeps track of frames that have already been accepted. If I send a frame here twice, so here ground will be sending frames 2 times. Sorry, it's from space. So we're sending a frame here. It's coming from the link proxy. We're playing it twice. What happens here is you're receiving it on this endpoint. It's accepted first. The process security does its job. But the second time it's played, so you receive it here again, exactly the same frame, is going to be rejected, especially because the sequence number is the same as the one that has been accepted before. So some attackers can be trying to think outside the box. What if we try to modify the contents of the frame? They may know where the sequence number is, they try to modify it, or sometimes they would think that we can change also the contents of a frame to affect what the telecommand does. In this case, well, this is where the authentication comes in. The frame will be rejected simply because it doesn't pass authentication tests at the receiving end. So here, we're sending a frame from the ground. The next 5 frames are sending are all randomly altered. And what you're seeing is from the space endpoint, all the frames are being rejected. And we're done. So, last case figure I want to show you quickly before I'm wrapping up. We also have the possibility that we can consider that the link proxy in the middle intercepts frame and attempts to send them in an alternate order. So what will happen here is also the same thing. The sequence number guards against this type of issue. The most recent frame would be accepted, but all older frames, by older I mean having a sequence number inferior to the frame that has been accepted, would be rejected. So here, what will happen is I will be intercepting 5 frames that are sent from the ground, and they will be sent in a random order to the satellite. It's taking a bit. And there we go. So the frames are sent, and there you go. So here we have the frames of sequence number 4 and 5, which are accepted, and then 3, 1, 2, which come at varying in a varying order, are all rejected because the sequence number has been already accepted as the receiving endpoint. It's important to note that the sequence number is always updated according to the last received and accepted sequence number. So this will conclude my not live, unfortunately, because of the issues we've been facing, but this concludes my demonstration. Before I wrap up, just a few things. So what you've seen here with the demonstration are a few things. We've seen nominal transfers, which show confidentiality of data. And second, you've seen that we can be resistant to replay attacks. We are resistant to permutation of frames, and we are resistant to frame tampering. So to summarize all this, so as I mentioned, security, satellite services which are deployed through satellite infrastructures are critical. Sometimes they're becoming part of our critical infrastructure more and more, and they have to be secured. They come with the unfortunate weakness that they are, they multiply the endpoints. We have a lot of ground terminals, we have a lot of satellites, so it's a wide attack surface. So we offer Satlink as a solution to this, which is easily implementable by anyone. The advantage is that you can already secure missions that are already deployed in orbit, but they are not secure yet. And so the advantage is that you can ensure three things: the integrity, authenticity, and of course the confidentiality of data. We've shown a demonstration, and then in this demonstration, nominal situations between the board of the STM32 and the cloud container. And now we're looking for the next step, which is to fly aboard an early adopter's satellite to test the solution in live orbit. So, if you want to get a head start with us, don't hesitate to go to the booth, the CYSEC booth over there. And also, one important thing is we're open to hire anybody who is interested in collaborating with us, which is either for a Satlink or other types of products. So feel free to drop by the booth later on and say hi. Thank you for your attention.
Okay, thank you very much, Luis. So our first question is from Hao Li. I will try to present it to the screen. Is the key unique for each ground station or shared by all ground stations in the same constellation?
So this is a good question. Thank you. So the keys have to be shared between all the ground stations for this to work. So this comes evidently with a key management solution that has to come with the service. So no, all the ground stations are sharing the same keys.
Okay, thank you. The next question is from Sylvain Barbu. Sorry if I don't pronounce the name correctly. And the question is, TM flux is usually very repetitive. What is the induced correlation of the encrypted packets?
That is a very good question as well. I'm not a cryptographic expert. I'm more on the flight software side. If you have questions about this, I request that you come over to the booth or write to me directly, and we'll discuss this further.
Okay. Next question. From the same person, what is the overhead of encryption in terms of memory usage on board and to the COM bandwidth?
Yeah, this is a very pertinent question. Currently, as I mentioned, the cryptographic backend is up for implementation by the adopter. We have a software implementation. We haven't tested yet the size and the CPU overhead. But currently, we're hoping that the clients have their hardware, for instance, a cryptographic backend, which they can use to accelerate the cryptographic algorithms, or they have their own software solution.
Okay. There is one more here. What are the advantages of the flight software library compared to hardware integrated solutions providing the same services?
So, it's not a all pro, all con solution. Instance, but there are quite a few advantages of having a a software solution. First of which is you have the possibility of updating already existing missions. So missions that are already deployed can be updated, provided they have the capability for software updates. And of course, the advantages over hardware is that the hardware comes with mass that you have to launch. It comes as a critical point that is vulnerable to radiation, and it adds complexity to the satellite bus because you have another endpoint that you have to communicate with. So that's the main advantage I can share for the software solution.
Okay, thank you. And some more are coming. So from Josie Roberts. How do you prevent the keys from being compromised when deploying your solution with a mission that is already flying?
Excellent question. So, as for this, same question as earlier, I'm not a cryptographic expert, so I will not get too much into wet grounds here, but there are solutions to deploy keys through encryption. I think there are ways to deploy keys in this manner. I would suggest you would come and talk with the booth with our cryptographic experts on this topic.
Okay. And the next one from Matei Florent Oana. What are the minimal hardware specifications components that have to be built in the satellite bus to be able to deploy ERCA while the satellite is in orbit? For example, is an encryption unit required?
All right. So I mentioned that you can use both hardware cryptographic backends for acceleration of the algorithms, but also software backends. We are developing our own software backend that you can use if you want to. Well, it will come as a cost to program memory, but you can also have your own. So minimum hardware specs, it's hard to say. It's really going to be dependent on what the client needs, and this is what we're aiming for, is compatibility with as many potential satellite integrators as possible.
Thank you. Next one, from Hugo van de Pol. What technology are you using?
So, it's software. So the library that is developed, at least for the ground station, is developed in Rust. So if you're interested in Rust, well, there you are. There was a very interesting talk about this yesterday. As for the software library that is deployed in space, it's not done in Rust because we want to have qualifications that allow us to ensure our clients that our software is of good quality, and this would be developed as a C software. That's it. In terms of technology, that's
Okay.
as simple as this.
Is there any question from the audience here? Yeah, Antonio.
Better for the people who are online.
Hi. Okay. So in the demonstration, you use authenticated encryption, but do you support authentication only and encryption only?
Absolutely, and this is well, this is supported by the standard itself. I showed a demonstration here with authenticated encryption because we believe this is the best way to go. We have doubts about encryption only, or only authenticating can also be useful in some cases, but they're all supported by the standard. So we are aiming to support a wide variety of algorithms as long as we have access to the cryptographic backends that allow us to implement them.
More questions are coming. What is the performance you guarantee telecommands per second, bits per second?
Okay, this is a question that is entirely dependent, no, not entirely, but very dependent on the hardware the software is running on. So it's hard to answer properly. But I can say that at least for the ground endpoint of the Rust library, we haven't seen any impact, massive impact on the bandwidth. The major impact will not be from the cryptographic algorithms themselves, but more from the added frames that you added data onto the frames you're sending. You're sacrificing a few bytes of from the bandwidth because you're adding the header and the trailer from the security standard. For the solution I showed you earlier with AES-UCM, it corresponds to 30 bytes of data. So if you have frames that are up to 1,000 bytes, you have a 3% overhead on the bandwidth.
Okay, next one. Do you plan on supporting other cloud providers than AWS or on-premise infrastructures?
So absolutely. I mentioned Amazon Web Services as a cloud provider, especially for the demonstration. This is because some of our early adopters and people we work with want to work with AWS, but our intent is to be well, available and compatible with other providers such as Azure and others.
Thank you. I have a couple of questions. I guess this is a commercial library, correct?
It's a commercial product, yes.
Yes. And you demonstrated some security assessment functionalities. If I recall correctly, it was replay, etc. Have you implemented or are you planning to implement features like performing, let's say, some kind of fuzzing through the library or buffer overflow attempts, etc.?
Absolutely, it's already underway. We're trying to have as much testing of the software as possible. As I mentioned, we want to have qualification of the software. This comes with a lot of validation testing, and fuzzing is part of what we have in mind.
Okay, thank you very much. Any other question from the audience? No? Okay, thank you very much.
Thank you very much.